Good morning, good afternoon, and welcome. My name is Mark Richardson with Vibration Technology, and we welcome you all to another MEscope videos webinar. I'm joined by my father, Mark Richardson Sr., the CEO and founder of Vibration Technology. And today we are going to look at using a GoPro camera with MEscope videos. And you might be thinking, wow, how are you going to use a GoPro? That's just a kind of a cheap camera that, you can, aren't they used for action sports and so forth? But actually the GoPro camera has come quite a ways in the past few years. And there's some great technology built into a relatively inexpensive camera. And we're going to walk through some of the features with the GoPro, and we will give some samples of capturing a video with the GoPro, and we'll go through the settings, and then we'll get into the MEscope video software and run through a little bit of the setup in there and how you process a GoPro video. And then we'll also talk a little bit about the comparisons between a GoPro and a cell phone, which traditionally is one of the more useful, and everybody's got a cell phone with them. So there's some pros and cons, obviously, to using either one. A couple of housekeeping items before we get going here. We are recording this video, so we will provide a recording at the tail end of this. We'll get it posted up on our YouTube channel. If you have questions, we should have some time at the end of the webinar, so you can type your questions into the Go to Webinar dialog box there on the right side of your screen, and we'll get those questions answered at the end of the webinar. With that, let me hand things over. Dad, let's take it away. Let's look at some GoPros.
Okay, thanks, Mark. As you see in the title here, we got two words in the title: GoPro camera and MEscope videos with a trademark. And that is a fairly new package that we sell. It's a different software package than our traditional MEscope VES, which stands for Visual Engineering Series. And that series of software has many options. MEscope Videos doesn't have any options. It's just designed to process videos, and you'll see the user interface is different than MEscope VES, for those of you that are familiar with MEscope. It's still Windows, but we redesigned the user interface so that it can be used in a touchscreen computer. So you can take the computer, an iPad or any kind of a portable battery-powered computer, and a GoPro, and of course your cell phone, out into the field or the factory, and you can start recording videos and look at the animation and extract the vibration from the videos right there on the spot. And the advantage of that is you don't have to set up with floodlights or anything like that, and power cables. Traditionally, if you're doing accelerometer testing or using accelerometers, you have all these other setup issues to go along with collecting vibration data. This package will allow you to do a lot in the field. So I'm going to go through some PowerPoint slides, and then we'll get into using the software. And I'm going to spend, let's say, the second half of this webinar, hopefully not more than the first half, with these video or with these PowerPoints, looking at some videos, talking about how videos can be used to get a quick look at vibration, show it to plant management, show it to your customer, your client, and then perhaps go on with a more detailed acquisition of data with accelerometers and shakers and so forth. So let's just go through some of the features. Now we're calling this enhanced video animation because that's what this software does. It processes a video, and the video can come from any camera. There are some very expensive ones out there, but as Mark mentioned, a GoPro is actually cheaper than a cell phone, $300, $350, and the technology has really improved with GoPro so that they can take videos in natural light in many situations. Now, the video we're looking at here was done with a cell phone camera. Again, no floodlights or anything other than your cell phone. So you get a first look at the machinery in the plant or the field. EVA makes vibration more understandable for technicians, plant management, or clients. EVA allows you to see vibration that cannot be seen in the raw video. So we can amplify it, we can slow down the motion, we can speed it up, we can do lots of things with the data once we've extracted it from the video. Problem with vibration, and the reason we've used accelerometers forever in testing for resonances and so forth, is that vibration occurs at a very high frequency. Resonances get excited in a mechanical machine or a structure, and you can hardly see anything with your eye or with a raw video. And the displacements can be very small. So those are the two things. We can control speed and magnitude of the vibration. And I'll talk a lot about ODS, operating deflection shape. And what we mean by that is as soon as I have motion at 2 or more points and directions, we call them degrees of freedom on any vibrating test article, we call that an ODS, because now we have a measure of the relative magnitude and the phase between 2 or more points on the structure. So we call an ODS. And the other thing is we talk about resonances a lot. MEscope was designed for modal analysis. My background goes way back to early days of working at Hewlett-Packard. It used to be an instrument company. And we used FFT analyzers and accelerometers and hammers and shakers to excite the resonances of a structure. But here we're talking more about operating data. So that's the advantage of a cell phone or a GoPro video. It displays parts that cannot be instrumented. We can display problems, vibration problems that occur during normal operation of especially rotating equipment. And we'll talk about orders. A rotating machine is going to have peaks in its spectrum at the running speed of the machine and then multiples of the running speed. We call those orders. And then a video is two-dimensional, and sometimes vibration can be tricky. It can vibrate, resonance can vibrate dominant motion in one direction, and then we go to a different frequency, and that resonance has dominant motion in a different direction. So that's why we use triaxial accelerometers to try to capture all that motion and understand the resonant vibration. The other thing is there's too many moving parts on this machine to put accelerometers all over it, and yet the video can capture the vibration. Once we've extracted the data from the frames of a video, now we use an algorithm, and there are a number of them now, and of course you're all familiar with the term AI, artificial intelligence. I own a Tesla. My Tesla extracts data from 8 different videos on the car in real time and displays the results on the computer screen inside the car. So it's the same thing that we're doing here with videos, and we're extracting vibration both, and we call them complex valued. The ODS, again, the operating deflection shape, has magnitude and phase. So various parts on the structure can have different magnitudes and phases relative to one another. The GoPro is smaller, cheaper, and complementary to the cell phone. So I'll bring that up. The GoPro software is an app that can be loaded on your cell phone, and you can completely control the GoPro camera from your cell phone. You can look at what it's capturing, you can start the animation or start the capture, stop the capture, and then there's just all kinds of settings in a GoPro, way more than you would find in a cell phone. Cell phone's a little easier to use, but the GoPro is more flexible. Now, the issue with more expensive digital video cameras is this issue of simultaneous sampling. In a GoPro or in a cell phone, the pixels are not sampled exactly simultaneously from the top of each frame to the bottom. It's a raster scan, kind of like the old TVs that scanned a beam from the top to the bottom. But the phase difference, the time delay, and of course the cameras are getting better all the time. We can assume that all the pixels are being simultaneously sampled. So if you're concerned about that, you can spend $10,000 or $20,000 for a more expensive camera. Vibrant resells one that not only will sample at higher frequencies, but is completely simultaneous from top to bottom of each frame. The difficulty with that is when you're sampling at a higher frequency, you need to put more light. You need to use floodlights. So that's the trade-off. You don't need to use artificial lighting with a cell phone or a GoPro, and you can get very usable results. So in most operating machinery, you can't shut it down. The operations people don't want you to shut down the machinery to do an impact test with accelerometers and look at resonances, although that's commonly done for problem machinery. Again, these are low contact or non-contacting, low cost, no contacting with the test article. So that's a real benefit. We can get videos of hot and dangerous machinery, or let's say in a nuclear power plant where you can't go near the machine, you can get a good video even from a distance. TWFs, that stands for time waveform. We extract the horizontal and vertical motion at a rectangular grid of points. And those are extracted from each frame of the video. So we're going to go into that. This is unique to MEscope. Other people who process videos just work with the pixels, and there you're talking about millions of pixels. We reduce the data set down from millions of pixels per frame to thousands of points in a grid, and then we do the animation. These animations you're looking at are from the points in a point grid that, and then the video frame is laid on top of the point grid, and that's how we do the animation. A little bit different than our competitors. So we can look at time-based ODS by sweeping a line cursor through the time waveforms, or we can look at order-based ODS. So what you're looking at here is a complex valued order-based ODS animation where we're using sinusoidal modulation and a peak cursor at one of the order peaks in the DFTs, another buzzword, digital Fourier transform. So the software does that very quickly and automatically in MEscope. Here's the other thing we can do with a point grid, which you can't do necessarily with millions of pixels. We can pick points very easily in the point grid and display data from the frequency domain, and we can integrate and differentiate in the frequency domain by using algebra. So that's a real benefit of using a DFT, or what we see up here, ODS-FRS. Now, that's a name that we have coined at Vibrant, and ODS-FRF obviously will allow you put a cursor in a set of ODS-FRFs and you can see the operating deflection shape at that frequency. Another explanation for that, we don't compute it that way, but a good explanation to understand it is the magnitude is the auto spectrum of the response, and the phase of the ODS-FRF is the phase relative to a reference response. So if all the points in the grid are relative to a reference, then they're all relative to each other. So you can see the little phase diagrams here in this video. In the X direction, which is the horizontal, the phase of those 2 points are 180 degrees out of phase with one another. But in the vertical, they're almost in phase with each other. And then you can see the magnitude, the inches per second of the frame on the bottom is over 1 inch per second. And of the coupler of this particular machine, it's a blower. The vertical is 1.85 inches per second. So it's really moving. So we can scale this data once and we'll get into that when we look at MEscope videos. Now this is a kind of a marketing video. Apparently the sound doesn't show up, so I'm not going to click on this link, but you can go out on, there are just tons of videos out on YouTube, and this is a YouTube video. I'll just start this and we'll stop it real quickly, but it's a marketing piece that shows you what the GoPro, and the latest one is, well, let me just put it back here and show you. This is the one that I bought that I've been using. So you can see all these different features. It's just loaded with features for making videos. So there it is, the 12 black, and it's, we'll just go on from there. And let's go back to, well, let me shut that down and we'll go back to the webinar here. Okay, so as I said, there's just a whole host of settings that you can set up from your cell phone in the GoPro camera. So the GoPro camera is tiny compared to a cell phone, and it can store hours worth of videos. So you could walk around in a plant and do a route-based data collection of the whole plant with one GoPro, and then save all the videos in the GoPro and then upload them to your computer, either in the field or back in your office. But you can see all these different words, super view, wide view, linear, which is what we would typically want if we're gonna, those are the straight lines, so we don't have so much perspective. Linear plus the horizon, you can stabilize the horizon in your video. So there's just a lot of features. The 5.3K is very high resolution. That's even higher than a typical cell phone. Cell phone videos that we typically make are 4K. That's 4K by 4K. So that's a lot of pixels. And then the different frame rates. And this is the other limitation of a cell phone or GoPro, that they will only sample up to 240 frames per second. But that is 14,000 RPM. So that covers a lot of machines. Now we'll look at that and we'll talk about that in a minute. So here's the different aspect ratios. And so the highest quality is a 5.3K, and that is 16 million pixels per frame of the video. And we're gonna process some at the basic quality, the 1080, and maybe we'll even look at some 4K. I have some of those that are typical of a cell phone video at 12 million pixels per frame. So here's a little test article I have in my office here. I've got several of these. It's just a rotating machine, and we can you can see these little screws. You can screw the screws into the different rotors and simulate different unbalances. And we have software in MEscope VES for identifying, based on the ODS of the machine, saved in an archival database, we can identify different unbalanced cases. So a lot of machinery maintenance stuff. I'm going to show you a video I took. This is another little handy device where you can put the GoPro around your neck. And I tried doing one standing up. The problem is your heartbeat shows up in the data, or not your heartbeat, but your breathing. I'll show you that in a video, but you also get the vibration of the machine extracted from the video. So what are we talking about here? Cell phone, low cost, non-contacting, and same for a GoPro. The GoPro can completely be controlled by your cell phone, so you don't have to touch it, and there's no jitter from touching the GoPro. And here are the different sample rates. Same for a cell phone, 30 frames per second, 60, 120, 240. But when you convert those over to RPM of a rotating machine, those are half. And we call that the Nyquist frequency. So I get a spectrum up to from DC to 0, or 0 to 900, 0 to 1800. Most of them we're going to look at here are 0 to 1800 RPM, but we actually have software we can unfold out to 3600 RPM, which is the sample rate of 60 FPS. 60 times 60 is 3600 RPM sample rate. Simultaneously acquired, I mentioned that, we won't go over that again. In the frequency domain, once we've got the spectrum data in the form of a DFT or an ODS FRF, we can integrate and differentiate. So here we've got a video on our website where we compare accelerometer data with displacement data from a video, and when we differentiate the displacement data, integrate the accelerometer data, we can match them up in velocity units. The other advantage we have, we can look at things in the time domain, and we can look at things in the frequency domain. Okay, here's a price list. Here's what we're talking about. ODS videos or MEscope videos is a separate package. And here's the 12-month license for one computer, $6,000. For a network license with one seat, $7,500. So it's relatively cheap. And then local language, add that on. We also have a service that we offer on our website where you can just take a video with your cell phone or a GoPro and then upload it, and with a credit card for just a few $100, we will process the video for you and do a video recording of the computer screen and send you back a video of the ODS animation, both in the time and the frequency. So let's put that down and go and take a look at the software. So here it is. Here's MEscope videos, and I've already processed the video, and I'm animating from the DFTs. You can see them down here, and there's virtually thousands of them in this data block here. If I go up to the and just click on the time waveforms, these are the TWFs that were extracted from the raw video. And you can see there's even a little bit of a blur here because I put some of those unbalanced screws on the outer rotor just to make it shake a little more. You can also see that I've got down here, these are in inches per second, so relatively quiet vibration of this machine. Now, what's this other peak doing in here in the spectrum? Well, that is an aliased. Let me go up here and see if I can. I've got to move things over here just a little bit. And I'm going to turn on the aliased orders. So that is an aliased order. Well, if this is the running speed of the machine at 1300 RPM, what is this peak? It's folded around 1800 RPM. Remember, this data was taken at 60 FPS, which is 3600 RPM. Half of that is 1800 RPM. And that other peak here at let's just see what the frequency is. It's 970 RPM. Well, if I take the second order, which is what, 1300 times 2, the second order is at 2600 RPM minus 1800, which is the Nyquist frequency, and that's 234 RPM. So if I subtract that from 1800 RPM, let me do that one again. 1800 minus, anyway, you get the idea. I'm not doing the math very well, but the software does it, and you end up at 970 RPM. So that is the second order of the machine. I can go over here and crank the amplitude a little bit, and you can see, well, I've exaggerated a lot, but now if we zoom in, you can see this machine is behaving like almost like a mass on a spring. Let me just go over here and blow it up a little more so you can see. So now you can see the base is just rocking around on the rubber mounts of this machine due to this unbalance. And so let's just go back, and let me just get out of this one, and let's just go back and start with a raw video, because I want to show you how we go through raw videos and process them in order to get the animation we just looked at. Okay, today's videos. Well, let's just go back. These are labeled here. So here's one that I took earlier, 4K with one unbalanced screw and 60 FPS. So let's just go through and look at that one and see what it all looks like. Okay, so here is the video that the GoPro took. And the first thing I want to do is crop out all the background. So, because I'm not interested in any of that. And again, this is, I'm not sure whether this was 4K. Well, it's 4K, so 2 million pixels, but now we're limited to, and then the first thing we can do here is change the brightness and change the contrast. So the contrast has been increased to the maximum, and I can change the lighting. Obviously, I don't want to go too light or too dark, so right there in the middle is a good spot. And I can recrop. If I was only interested in the motion of these bearing blocks, then I could just go and crop here again, just using the bearing blocks, and that would use even less of the, well, I'm not sure why we're not being able to crop. So let's go back. Let's start over again here. If I just wanted to really focus my attention on what's going on there, or even, let's come back. We'll come back and do some of that. Let's just go through and process this, and I'll show you the steps. So I'm going to hit the next button here. And now we set in the frames per second, which is already set to 60. And here I have a slider that tells me the frame count. I've got 1,272 frames in this video. And here's the beginning frame, and here's the ending frame. It also says that I've got 21 seconds of data. Now, if I divide, one of the rules of the FFT in the frequency domain is that delta F, my resolution between samples, is always equal to 1 over the time length of the video. So what's 60 divided by 21? That's about 3 RPM. So we got 60 frames per second, or 60 RPM, which is the sampling rate, divided by 21 seconds. And so my resolution in the frequency domain is going to be about 3 RPM. Let's cut it down. We can actually get very good results even if we only use 10 seconds of data. So you don't need much data. So here's 11 seconds of data, 600 frames of the video, and let's just go ahead and process it because it'll process more quickly. Now here's the point grid that I talked about, and this is unique to MEscope. Rather than look at the raw pixels themselves and average motion and so forth, the software will average the motion of each surrounding point in this point grid, or the pixels are surrounding each point, and that is what we will extract as a time waveform for each point. And then we'll get a vertical and a horizontal. But let's just crank this up. We'll take it to the maximum. I can have 13,000. Well, that's an awful lot. Let's just back it off a little bit here. If I'm only interested in the motion on the top of the motor, you can see we've got some mounting places here where we've put accelerometers, and then you can see the accels. There's actually 2 triaxial accels mounted up here on top of the rotor kit. 7,800, that's going to give us now, if we start the extraction process, and we'll see here, it's going to take, okay, it's going to take a minute. It's going to take a couple minutes. Let's go back and we'll shorten it up here just to get through this a little faster. Okay, next. Let's go with fewer frames. And okay, so we got about 10 seconds of data. The frames are what take the longest, so we can cut this back. And what this will do is cut back the number of time waveforms and DFTs, digital Fourier transforms, that we extract from this video. So we'll go back here and reprocess a few times. So this has taken, again, a couple of minutes to process. Okay, that's too long. Let me go back and get a different video, and you'll see how much faster it is if we go with the 1080. So here's a 1080 video with, okay, so bingo. Here it is. So let's crop that one. And we'll just work with the 1080s from now on here. Okay, well this has only got 6 seconds of data. So this is a very short video. Let's just go ahead and process it. I'll crank the number of points up here so we can just get some more data from it. Now, a lot of these points we're not interested in. We're really only interested in some points on the machine. So this is why we do this processing, to limit our analysis to just the time waveforms and the DFTs of the machine. So this one's relatively quick. Again, there weren't that many frames. Okay, now here's where we set the distance. This is where we can scale the pixel motions. And if I do that, if I say select distance, I know in this case that the distance between these outer edges of the 2 bearing blocks is 8 2/3 inches, so 8.62425. There we go. So that's the actual measurement, and this will scale our data. So if you pick any 2 points in the video that are relatively close to the plane of the video frame. So I could come down here, set distance. I don't know what this distance is right down here if I knew what it was, or I could even put a ruler, let's say a yardstick, and on the table in front of this machine or on the ground in front of the machine. Once you have this number, then you're all set. Let's go back and put in the number that I measured and that I know is the true distance here. So I'm going to put in the 8. Okay, so now this is a histogram of the data. So we've already extracted all the time waveforms, and this is just showing us, this is a count of the low frequency, the low amplitude says point count here, all the way up to there's 100 bins here of the maximum motion. So let me just click this up and take out that first lowest frequency. You see it took out all these background points. They're not moving very much frame to frame in the video, so I'm not interested in them. Here we're taking out a bunch of points because the algorithm can't tell the motion of the pixel from one frame to the next because it's all the same color. The algorithm is based on a color difference, black and white, or in this case, actual colors between one frame and the next. If I take out the high motion, let's just take a bunch of those out. Now you can see that it took away some of the motion on the top of the rotor here. It took out some more points of the black base. We could take those out of our analysis, and what that means is we're going to get no TWFs or DFTs for those points, but at least leave these in because the animation is going to get very distorted here if I take some of this high frequency or not high frequency, but high amplitude. So I want to see the motion of this rotor here, but I don't care about anything out here in the background. So I'm going to finish. And the next thing we're going to see is the animation. So there we are. There's the animation it's a sweep animation of the time waveforms. You can see there's just, I'll drag down here, there's just thousands of them in there. And those are the ones for the points that are still, that we didn't remove based on, the background over here. Let me go and, well, let's go down here and just look at what we have down here, because this is what we looked at earlier. I'm going to turn on the peak cursor and put it around one of these peaks. Let's just put it around this peak here. Okay, that's the 900 RPM. That's an aliased peak. Here is the running speed of the machine, 1300. And if I turn on the aliased cursor again, I can see the aliased second order. So this one is really, it's not at 900, it's at 2600. But you can see a very clean ODS of the machine. And if I go through here, well, let's just do some more analysis. I can actually put the motion of these points. So if I go over here and select edit point graphics, and I'm going to edit magnitude and phase labels, and I'll click down here. This is my point selector. So I'm just going to pick a point here and a point here. And I'll say accept that. So very quickly after getting this video, I can, and extracting the motions, the time waveforms, and now I go up in here and deflection. I'm going to turn on the magnitude and phase. So there it is. There's the inches of motion of the frequency ODS. Let me go back and we'll turn on a different cursor here. So we're looking at inches. You can see it's 0.009 inches. I have another selection up here and I'm going to show it in velocity. So there it is. There's my velocity. Close this. There's my velocities and phase of those 2 points. Again, the y direction, which is the vertical, they're in phase with each other. So they're just, this machine is just bouncing up and down like a mass on a spring. And in the x direction, the horizontal, they're got some slightly different phase. So let's go back and process another video. I'll just take you through this again and very quickly. The 4Ks are going to take a little longer. Here's a 1080 with 3 unbalanced screws. So again, there's a video. We want to crop it. Don't want to look at all the other stuff in the background. Now again, this is a little blurry. If we went to the higher resolution, it would be a little clearer, but we just don't really need to in order to see what's going on. Okay, this video is 20 seconds long, so I can shorten that up and that would just use less frames. So let's just use about 1,000 frames. Now, 1,000 frames is going to give us, well, 14 seconds. Let's get 15 seconds. So that's going to give us frequency resolution of 60 RPM divided by 15. So what is that? 4. That's going to give us about 4 RPM resolution in this spectrum. Okay, we got 10,000 points. We don't need that many points. Let's cut it down to something that's a little less. You can see, you know, we can just a lot of different things we can work with here, but the 1080, see, it only takes less than a minute. So if I'm out in the field and I just want to check my video, bingo, I can do that very quickly. And so we'll race through this one. Mark, are we getting any questions? Did you ask them about questions?
Yeah, if you got questions, go ahead and get those typed into the question box there. We don't have any questions right now.
I am by no means an expert at using a GoPro camera. This is based on a very short amount of time using the GoPro. And again, this is something just like using an FFT analyzer. The better you get at it, the more accurate your results are going to be. But if you just want a quick look at the enhanced video animation, that's what I'm demonstrating here. I'm going to take out a few of these low amplitudes. This is the amplitude histogram. Remember, it's taking them out of the background. We don't care about the background as much. We're just really interested in how the machine itself vibrates, and that looks good to me, so I'm going to finish. And there we are. So there's that animation. Now we got a little bit of a change here, but this is a little less resolution. So if I put the cursor down here and I need to turn on the peak cursor again, here, let me set it around here. You might say, well, what's going on there? Well, let me just explain. I'm going to put on the the orders. And so here's the running speed. Now you see what it says here. This says DFT envelope. I've got thousands of time waveforms, and for each time waveform, I've got a DFT, a digital Fourier transform. So what this is the envelope, because a lot of these points aren't moving very well, and obviously the two rotors are the ones that are moving the most, and so that's why we see a little bit of a difference here, because some of the measurements, maybe not quite as accurate, are contributing to the envelope. Now this envelope is computed in the software. It goes through and it does what we call a peak hold average. And so it grabs the biggest peak as it goes through each of the measurements. And that's what we're looking at here. So we can see where things are. There's the second order. You can see that the vibration of the second order is quite different. There's a lot of deformation now due to those unbalanced screws. You can kind of see them in this frame of the video. Those unbalanced screws are both were screwed in just next to each other. Here, it's more of a mode shape. These are operating deflection shapes, but they're being dominated by the resonance of the two wheels. So if I go over here and just look at the animation, you can see a lot better. This is what we call, it could be called an operating mode shape. It is the resonance, and you can see how they vibrate differently at 1300 RPM. And then we also have motion of the bearing blocks. If I'm really using that data to compare with last week's data or any other archival data, the ODS data, and Vibrant has software for doing all those things. Anyway, I'm going to wrap this up. Mark, do we have any questions?
We got one question here. Have you ever compared analysis from compressed and uncompressed videos?
Not sure how to answer that one. Compressed, the
uncompressed, I guess.
In the cell phone, you can do a slow motion that just changes the frames per second. It bounces up to 240, and same thing in the GoPro. When you talk about compressed, I'm thinking more of how you store the video itself. You certainly want to uncompress the stored video and process it, you know, in the MEscope video software as uncompressed. Not sure how to answer that question.
That's all
we can go back and look at
right now. Yeah, maybe we'll have to get back to that one, Michael. Maybe
yeah.
we can dig into that a little bit more. And I bet you Sean would know the answer to that one.
Perhaps. Okay, well, I'm ready to wrap up unless we have other questions.
Yeah, if anybody else has any other questions. Again, we'll get these. We'll get this recording up on our YouTube video, YouTube channel. If you go out to youtube.com/Vibrant Technology, you can get a record. You can get a library of all of our old webinars, plus a lot of training videos as well on both MEscope videos and MEscope VES. Additionally, if you have any questions sales related, you can email us at sales@vibetech.com, and we can get you any kind of pricing questions you might have. Yeah, nothing else at this time.
All right.
Great.
We'll wrap it up right there.
Sounds good. Take care, everybody, and stay tuned. We'll get another webinar up for you next month.
Okay.
All right. Good day.